Hello, this is Mark Darnell with SUSE. Ryan and I will be presenting performance optimization, Rook on Kubernetes today. Real quickly, Ryan Tidwell is a senior network engineer with SUSE who works in one of my teams. I'm a principal product manager handling our SDI and platforms for SUSE. What we're going to be covering today is specifically running Rook, which is a containerized version of Ceph, on top of Kubernetes and doing some performance measurement or some benchmark evaluations of that technology. Quick intro, we'll talk about the benchmark environment, we'll work through methodology and results, give you some of those insights, and then discuss what we want future work to be. So as an introduction, why did we do this? Put simply, SUSE has been a long-time player in the open source space. We are involved in Kubernetes, we're involved in Ceph, software-defined storage, and we're rolling products out that will integrate those technologies via Rook. In order to integrate them, you need to ensure that you have a reasonable network stack in terms of performance to tie those together. And the driving component to do that is a CNI plugin. So we need to understand what CNI plugins SUSE should be including there to maximize customers' performance. And we want to make sure that as a good open source citizen, that we return those lessons learned back upstream into projects like Calico, Cilium, Multis, Network Service Mesh, and so forth. Real quickly, just to make sure that we're all operating from a level playing field, this is a slide from Rook documentation. Once again, Rook is a project which takes Ceph as a piece of software, containerizes it, and puts it on top of Kubernetes. So rather than running Ceph bare metal without any kind of orchestration in between, we actually have a 3-layer stack. In order to link those together, once again, you'll end up with a CNI plugin that sits underneath Rook in order to make sure that it's talking to Kubernetes and the network, the underlying network stack correctly. So let's talk about Kubernetes networking enough to ensure that once again we're working from a level playing field within the audience. Kubernetes networking works in a couple of ways. One is what you would call kind of the standard approach, and this uses a set of technologies that are part of both user space and kernel space in Linux. You'll create things like vEth pairs, you'll have MAC VLAN and IP VLAN, you'll talk to a physical interface. You may actually use an SRIOV virtual function as part of an SRIOV adapter. It also, for some networking models, goes through a Linux bridge virtualized switch. So there's a set of components that traffic must go through. This set of components will add overhead. A second mode that Kubernetes provides natively is called host networking. And what this does is this effectively opens up access from the device, the underlying devices, to the pods. It opens up access from the pods directly into host networking devices. It kind of bypasses a chunk of security that you would typically expect to have. So while performance tends to be the best because you're not running through any of that overhead that's listed there in the first bullet point, you do have a problem in the sense that you may be less secure. So SUSE, as we're rolling these products to people, we want to make sure that we provide the best possible performance while not compromising security. And that's part of what these benchmarking methodologies are for that we're working through. I'm going to go ahead and turn this over to Ryan. He's going to do some of the heavy lifting here and describe a lot of the work that he's done in this benchmarking environment. So Ryan, over to you.
Thank you, Mark. Let's start by just briefly talking about the environment that we had at our disposal to benchmark these different configurations. So this is a snapshot of the hardware specs that we have for our Ceph nodes and our client node. Got some top-of-the-line NICs at our disposal, as well as some really fast NVMe SSD storage. What I wanted to show here was to kind of set a level playing field. The first bottleneck you might think of would be the hard drive or the SSD itself. So the first thing we did was just benchmark the performance of these SSDs that we had in our storage nodes. These are the same SSDs and the same on the same motherboard and identical configurations across the cluster. So we first benchmarked that with testing write and read IOPS. I want to just point out something on this slide that might be useful useful to remember as we go on. With the write benchmarks, we notice that we start off kind of slow at 1K and 2K block sizes, and we believe this is just a function of not aligning to native block sizes, things like page tables sizes and that sort of thing. So keep that in mind. Again, I also want to point out here that we're measuring IOPS in terms of hundreds of thousands of IOPS. These are really fast disks, and the idea here is to not have them be a bottleneck in the system. So we're looking for the fastest disks we can get. This is just a snapshot of the software, the kernel, versions of Rook, things like that. The 2 bullet points I want to call out here are at the bottom, Calico and Cilium. These are the 2 CNI plugins that we tested. We grabbed Cilium and tested that. We do a lot of work with Cilium here at SUSE. This is also interesting from a performance perspective because of the BPF data path involved. Calico is also another popular tool that people use, and both support different encapsulation modes. And I want to call your attention back to Cilium and just mention that we're going to be testing with both encapsulated network traffic with VXLAN, and we're going to be testing a mode called Cilium Direct Mode, where we don't encapsulate pod traffic. For Calico, we're going to use IP and IP encapsulation and VXLAN encapsulation. So let's kind of look at the design of the cluster. At a logical level, what we wanted to have was just a single RBD client. We wanted to use Rook to deploy some mons and some OSDs, which are kind of basic building blocks of Ceph. Now, what this looks like when we deploy it from a physical perspective is a 4-node cluster, and we're ignoring the controller node right now. We're just focusing on the workers in the cluster. So we have 3 nodes that we're dedicating as storage nodes, and a single node that we're using as our client node. Now, there's a couple things I want to call out here. At the top in that top box, you'll see a FIO pod. Now, if you're not familiar with FIO, FIO is a benchmarking tool that we can use to run synthetic workloads on a storage system, whether that's a physical device or something that we mount through NFS, or in this case, Ceph. We're going to use that to gather our data. So we have a pod there that's acting as our client, and that's where our FIO benchmarking tool is going to run. Also want to call attention to the networking technologies real quick. We have 100 gig Ethernet networking available to our storage nodes, and a bonded pair of 25 gig NICs available to our client code. And we'll get back to the bonded pair of 25 gig NICs. That is an important part of the story that we'll talk about later. So let's move on and actually get into the meat and talk about the methodology that we went through and talk about the results. Before we do that, I want to set the stage with 2 basic concepts. I want to talk about latency, and I want to talk about IOPS. So first, let's talk about latency. As someone with a networking background who really works in the networking space, my first approach to this is to say latency is the enemy. What is latency? We're going to define that just very broadly as variable delay inserted by components in a pipeline. You can look to the left to see where we add latency in the system. So we'll start kind of from the top left and work our way around. first place that we can introduce some latency is in accessing the disk. Now, I want to point out this is something that your CNI configuration and your network configuration isn't really going to influence. That's going to be a pretty static cost in the system. The next bullet point is network transport latency. Now, this is the latency that's going to be incurred by emitting a packet on the network, having it traverse your top of rack switch, maybe a couple of top of rack switches, maybe a router. Depends on your setup. The idea here is the factors driving latency here are going to be bandwidth availability, congestion, bonding and switch configuration, and those kinds of things. And then the last bit is that kernel latency, the network stack that we have to traverse between the NIC and the pod. This is going to be highly dependent on our CNI configuration. And when you add this all up, the disk access plus the network transport latency plus the kernel network stack latency, you get the total latency. Our goal is to minimize the latency in both the kernel and the network fabric. Now, when we talk about the performance of storage systems, we like to measure things in terms of IOPS. Now, what's an IOP? Short for I/O per second. So a single I/O operation is going to incur all the overhead related to both the disk access latency and all those network-related overheads. The key point here is less network latency equals more IOPS. So the more we can drive down that network latency, the more efficient we can be with providing storage to clients. Because we talk in terms of IOPS and we think about storage systems, we're going to express these results in terms of IOPS going forward. So that's just a note to set the terminology. And now let's move on and talk about the methodology. So scientific method. This is kind of what was in our mind while we were trying this out. We want to change one variable at a time and hold all others constant. That variable really being the CNI plugin here. We want to optimize the base system, make that as fast as we can. So we've got jumbo frames, or a maximum transmission unit, or MTU, of 9,000. And we want to use the fastest disks we can so the disks are faster than the network. We don't want the network to be, we don't want the disk to be the bottleneck here. We want the network to be the bottleneck so that we can change parameters on that and see how those different configurations influence the performance of the system. As I've been alluding to, disk access time is effectively going to be a constant here, regardless of the CNI plugin used. And then we have a single RBD client running on a dedicated node, and that's where we measure the IOPS, where we're taking latency and peak bandwidth demand measurements. And then we run through this whole process, swapping out the CNI plugin or the CNI configuration, and rerunning the tests by changing that variable. So now that I've set the stage, let's dive into the results. So let's start by looking at read benchmarks. And I'm going to call out what I'm deeming common block sizes. So this would be anything from 1K to 8K block sizes. When performing a read benchmark with this single client, we observe a 20 to 25% overhead when using encapsulation. So both Cilium and Calico, when encapsulating pod traffic, are incurring pretty significant overhead. Now, I mentioned Cilium direct mode earlier. This is a mode that Cilium runs in. There's a similar configuration for Calico that we didn't test, but the principle still holds here. We're not encapsulating traffic, and we're not paying those overheads. And so, as you can see, Cilium direct mode actually stacks up quite nicely against host networking from a performance perspective. as opposed to 20 to 25% overhead, we're only paying about a 2% overhead, which is pretty impressive. So let's look at these larger block sizes. So anywhere from a 1 meg block size to an 8 meg block size. Again, we have significant overheads here when encapsulating pod traffic with VXLAN or IP and IP. 30 to 50% overhead relative to host networking. In the worst case, we see that the Cilium direct mode only at that 2 meg block size incurs a 10% overhead, but is much more competitive at other block sizes. Again, Cilium direct mode stacks up really nicely compared to host networking, and we're not paying that overhead with the encapsulation cost. So let's move on and look at the right benchmarks. So these common block sizes, again, 1K to 8K, we observed a 5 to 15% overhead when encapsulating pod traffic. Cilium direct mode still stacks up favorably. Again, we're seeing roughly 2% overhead for that Cilium direct mode, really competitive with host networking. And then when we look at those larger block sizes, the 1 meg to the 8 meg block sizes, this is where things got a little interesting, and we had to dig a little deeper into what was happening. We're only seeing a 1 to 2% overhead. In Calico, with the IP and IP encapsulation, incurs a little bit more overhead. But these are surprising results. Why does the performance not differentiate itself on write? This is something that we had to dig into. Now, if you recall in a previous slide where I was discussing the environment we had, I mentioned a pair of 25 gig bonded NICs that we have on our client node. And it turns out that this is an important factor that we didn't consider initially. But before we dig into that, let's talk about bonding a little bit and make it clear what we mean when we talk about bonding. So bonding is when we take multiple physical interfaces and we make them appear as a single interface with multiple channels working behind the scenes. Now, Linux supports a myriad of bonding modes. We were running with LACP bonding, might hear it referred to as mode 4. This is just the configuration that we had. In this specific configuration, LACP has some tunable parameters, and one of those parameters is a hashing algorithm for transmitting packets, determining which interface we're going to emit the packet on. That's done through a hashing algorithm. The key here is we want to figure out how we can balance traffic really nicely across these NICs. Again, we have two 25 gig NICs. This is a lot of bandwidth. Let's make the most of it. So how do we balance this? And it turns out it's these hash policies that matter. So bringing this back to the environment, our initial round of benchmarks, we observed that poor utilization on that bond. Our network bandwidth demands topped out about 25 gig when we had a second 25 gig NIC that we could have spilled over traffic to. So the question we naturally ask is, how do we drive some better utilization on that? Well, we had to tune these bond settings, and it turns out that the parameter that yielded the most dramatic results was tuning this transmit hash policy parameter on the bond. Now, let me just preface this by saying these are the settings that yielded the most dramatic performance gains in our cluster. So for host networking and Cilium with VXLAN and Cilium with direct mode, these are the configurations that we tested with the tuned hash policy. We had to tune them a little different because they have different characteristics in the way that they set up the data path. So, with host networking, we use this layer 3+4 hash policy, which what that does is that just takes into account your source IP, your dest IP, your source port and your destination port, feeds those into the hash algorithm, and determines which NIC packet goes out based on those parameters. For VXLAN, for Cilium of VXLAN, we had to use the NCAP 3+4. Now what this does is this does the same thing as that layer 3+4 bonding, except it looks inside the inner packet of the VXLAN encapsulation and uses the inner packet, source IP, dest IP, source port, and dest port. And it doesn't use the outer packet. Now, Cilium direct mode, we use the layer 2+3 hash policy, which takes into account the source MAC address, the destination MAC address, and then the source IP and the destination IP. These settings yielded the most dramatic performance gains in our cluster. Keep in mind, these are very specific to our cluster. Factors such as cluster size, bonding mode, hardware capabilities, they're all going to call for different settings, and you may need to tune things differently if you're going to use bonds. Now, what did this get us? Well, let's start by, again, looking at these common block sizes at 1 to 8K, and it was kind of underwhelming. We didn't really see much difference when we tuned the hash policies here. Turns out at these block sizes, we're not actually generating enough network traffic for the balancing of packets across the NICs that participate in the bond to matter. But when we move toward those larger block sizes, these 1 to 8 meg block sizes, we're actually putting more demands on the network in terms of bandwidth. And what this does is this causes us to need to spill over to that second NIC to utilize its bandwidth. And what we see here is significant performance gains by tuning these policies, as much as 40% more IOPS by making this simple change. And that's across the board, both the VXLAN encapsulated traffic as well as the host networking and the Cilium direct mode. One thing I want to point out here is, this is not a direct simulation of a cluster that's under load from multiple clients, but the fact that what we're doing here is demanding more bandwidth from the network. This is an indication that these sorts of bonding settings will matter if you have multiple clients using the network and putting packets out there and stressing the network. Now, another thing to point out here is you may not be using bonding. This may not be common on your client nodes. That's where the bonding in our setup was. But you may be employing bonds on your storage nodes. Again, the same principle applies. We want that good balance of traffic across the bonds that we're having, or the NICs that we're having participate in that bond. So we learned a lot from this. So let's talk through some of these insights that we had. So let's finish up talking about bonding. What to know about bonding? Again, this may not be something that you do in your environment, but if you do, it's something to pay attention to. And there's a lesson here that we learned, which is question your assumptions. We just assumed that we had a bonded pair of 25 gig NICs. That's 50 gig pipe, right? Well, that should be plenty of bandwidth. There shouldn't be a bottleneck there. Well, it turns out it wasn't tuned properly, and it did become a bottleneck. So it turns out if you're going to use bonding, these bonding modes matter. You want that balance of traffic. Again, these are sorts of configurations that are going to be specific to your environment, and factors such as your CNI configuration, your scale, hardware capabilities, they're going to drive your choices here. As far as general recommendations, some of these may seem basic, but again, these are learnings and things that were confirmed for us. Overlays and encapsulation are going to limit your IOPS because they're going to introduce latency in the network. So where possible, try and avoid encapsulating pod traffic with VXLAN or IP and IP or GRE. Pick your encapsulation protocol. That's going to add overhead. So we want to avoid that where we can. Bandwidth demands of a single client are going to be highly correlated with block size. We harken back to the slide I showed that had the benchmarks we ran natively against the SSD, and the right benchmarks kind of exhibited a strange behavior at 1K and 2K block sizes, and then all of a sudden, once we hit 4K block sizes, performance shot up. We want to align with a native block size. When using bonds, again, pay attention to those hash policies. And some of these minute details, tuning these things can yield significant performance gains, and it may not always be obvious where your bottlenecks might be. So again, question everything. And this experience that we had with bonding is a perfect example of that. So with that, I want to hand it back to Mark to wrap things up.
Thanks, Ryan. Really appreciate all the solid work there, and we believe it's going to set the stage for some great follow-up work that we want to present at following KubeCons. So let's drive one specific point home. Once again, we were really doing this work in order to determine, look, there are multiple CNI plugins you can use and multiple network paths that you can use in order to set this three-level sandwich of Ceph, Rook, and Kubernetes up. Primary lesson to learn here is, look, the best hardware without the best CNI is going to leave you wanting. Quick caveat, do we believe that we've covered all of the possible CNIs here? No, you'll see that momentarily in a next steps. Next lesson, host networking is easy. It's a little bit insecure. It performs well. It was really the target that we shot at for all of the tests that we did. So it's an excellent thing to kind of set the stage for where your system is, but it may not be what you want to actually deploy in production. Next, IOPS matter. And this one is one of those obvious statements of realize that storage people look at IOPS. Unnecessary network latency is going to hurt IOPS. So as a system architect, ensure that you design your architecture to minimize network latency. Next thing, Ceph actually implements policy enforcement. Why does this matter? Well, you have policy enforcement that can happen at the Ceph layer. You have policy enforcement that can happen at the CNI layer. And you will have some storage people tell you, hey, I've got this at Ceph. I don't necessarily need this at my CNI layer. One of the things we did not benchmark here was implementing additional policy in the CNI itself. And different CNIs have strikingly different performance levels. If you go look at talks between XDP and, say, IP tables, you'll see that point really hammered home. So realize that you may want to push implementing CNI policy in, which would actually make the performance gains even more striking in the benchmarks that we ran. So future work. One of the things we did not look at was Multis with SR-IOV adapters using virtual functions. Both Ryan and I, with our network background, believe that fundamentally that should not matter, that host networking should be the primary or the best performance case that you're going to be able to generate. We would like to test that, though. Next thing, Calico is doing some extensive work integrating BPF into their environment. So that would begin differentiating now between Calico and Cilium and using the same underlying technology, which would be BPF and XDP. We believe that would be a valid test case to start looking at. In addition, we would like to improve our inline instrumentation in terms of making sure we can actually timestamp from the time a packet leaves FIO and actually exits a NIC on the box. Right now, we have a round trip with FIO from the time it leaves FIO and goes down and back across and then returns all the way back to FIO. So it's a black box test that we're using right now, and we'd like to make that finer granule. Finally, we have 3 nodes in a cluster and 1 device driving a workload. While that's great for setting baseline benchmarks over time, we need to add more clients and more storage nodes in order to have cross-load interference. So we'll go ahead and open the floor for Q&A. I'm going to rip through this and we'll figure out how this works with our online format right now. Thank you for your time, appreciate your attention, and look forward to hearing back from everyone.
Okay, everybody. Thanks for joining. Happy to take some questions. We've had a few good ones come through the chat while the presentation was airing. So dive into a couple of those. One question that kind of popped to the top here was, how would I improve latency if I'm using NFS? And my answer to that would be everything that we talked about here applies to NFS as well. So whether you're using RBD or NFS, these same principles are going to apply. Another question, and this one is one that I wanted to spend a little time on. I wish I had spent a little more time on it in the presentation. The question is, how are IOPS bound by network latency? I would have thought that they were limited by bandwidth. And that's exactly the intuition that I went into this exercise with myself. I had 100 gig networking on my storage nodes, 25 gig bonded pair on my client node. I should be able to get amazing performance because I have all this fast networking available to me. And the reality is, at least in this setup, latency or bandwidth was not the driving factor for performance. And what it really turned out to be were these different configuration parameters that we discussed in the talk. CNI plugin and the way you configure it actually makes a huge difference. And what we're hitting there is that latency, both in how we access the network and in the kernel as we use different CNI configurations. You know, the other thing that I guess I should have known going in, but I didn't think was, you know, I'll just be able to fill this pipe if I tune it right. It turns out really the way to use all that bandwidth was actually to push larger block sizes. Now, of course, as you scale up and you start using as you have more clients using the cluster, regardless of the block size, as you scale that out, you're going to make better use of that bandwidth. But you know, bandwidth was not the determining factor in performance here, and it was these different areas where we have latency, both making sure that the bond is configured correctly and you know, minimizing the overheads and traversing the network stack. So great question. I appreciate that one. I didn't get to spend as much time on that in the talk as I wanted. See, the next question that came through in the chat, did you also measure CPU overhead caused by the network plugins? And when was there any? Yeah, there's absolutely CPU overhead here. And I'm sorry to say that's not something that we measured this go around. We were really focused on what knobs we can turn to drive IOPS in the cluster. So, you know, that's definitely something to look at going forward. I know that others have done work profiling Cilium and Calico and other CNIs. So you may be able to find some answers, maybe cobble that together. But I don't have those numbers right now. And that's something I would like to go back and look at. Let's see, what else do we have here? Can you say more about the networking equipment which was used in the benchmark? This can have a huge impact on the results. Yes, so we had, as I mentioned, we had both Mellanox and QLogic NICs at our disposal running at 25 and 100 gig. We also were connected to a I believe this was a Dell switch. I would have to double check with my storage engineers. Again, 100 gig networking off the switch. So yeah, basically 100 gig network fabric, and then my client node was only able to run at 25 gig. Let's see. For future tests, we look at production clusters and the block sizes they are doing for reads and writes to get more realistic benchmarks. 1 to 4 meg block sizes are nice for filling your pipe, but not for IOPS. Yeah, absolutely. The 1 to 4 meg, that definitely fills the pipe, puts stress on the network, and kind of the reason I scaled up there is I actually profiled the characteristics of different block sizes just as something to explore, to kind of see what the impact on the network was. And it turns out that that turned into a sort of a proxy for scale in the system. It's not a perfect one, but it puts more network traffic out there, and it's more for the system to handle. So it's sort of a proxy for scaling up with multiple clients. Obviously, as we talked about in the talk, just having a single client out there is not realistic, and that's one of the things that we're looking at is doing this exercise in a scaled up environment where we are using more realistic block sizes, we're using a more realistic number of clients and a more realistic configuration. This exercise is kind of a first pass to build kind of a basic understanding of what the key factors we need to pay attention to with regard to performance are. So yeah, thanks for that question. All right, well, again, thanks for attending and thanks for the great questions, everyone. We can move this conversation over to Slack, and I'm happy to take questions there.